something called a Java FutureTask. And so here we'll talk about what a future task is and how it's used to convey the result from a thread that's executing a computation to one or more threads that want to retrieve the results of the computation. So that's one thing the future task does that we'll cover. And then we're going to talk about this really, really cool helper class called the Memoizer, which is something called memoization, which always sounds like Elmer Fudd has said it. And we'll talk about what a memoizer is, and we're going to talk about its implementation and how it uses FutureTask to speed up programs by caching the results of expensive function calls, like computing prime numbers, and then returning the cached result again when the same inputs occur henceforth. So I'll show you that. It's really neat. But first, let's talk about what a future task is. So as I've said before, a future task is a way of conveying a result from a thread that's executing a computation to one or more threads that need to get the results back. That doesn't really provide much insight yet, but we'll talk about more things that it does, and then you'll learn why it's so cool. So a future task, as shown by this class diagram, implements something called a runnable future, which is an interface that in turn implements or extends future. So runnable future has everything in future, and then future task has everything in runnable future and future plus a few more things. So it provides a number of capabilities to programs. So one thing it provides is the ability to start running a computation, because it's a task, so you can run it, or it's a runnable, so you can run it, and you can also cancel it. So those are some things you can do with a future task. You can also check to see if the computation has completed or whether it's been canceled. Those are sort of future operations you can do. And you can also retrieve the result of the computation. And something that isn't shown here, but we'll talk about, is you can also have a hook method that's called back in order to be able to do something when a future has finished running, a future task. So here are the key methods in future task. So the constructor of future task is given a callable, and that callable is what's going to be called when the future task runs. So when the future task is run, the callable is going to be invoked to do its thing. So remember, a callable is a two-way operation. You can check to see whether the future task is finished normally by checking if it's done or whether it's been canceled. You can cancel a future task, which you can tell it whether it should stop the callable from running if it's running. You can get the result. This particular call will block until the task is finished running. There's also a timed version. It'll bound the amount of time it'll wait before it gives up. The run method actually runs the task, and what this does is it goes ahead and it calls the callable, and then when it's done running the callable, it takes the return value and it sets that to be the result of the future task unless it's been canceled. And then finally, there's this hook method called done, which is called back, and you can override this method to do whatever things you want to have happen when a future task is finished. And we'll see how that gets used for other stuff in a minute. OK, so that's basically what a future task is. Now, it still may not be at all clear what the heck a future task is good for, even though I've explained to you its interface and talked briefly about what its methods do. So to make it a lot more clear and a lot more obvious why it's a win, we'll talk about applying future task to something called the Memoizer. Now, what is a memoizer? Well, memoization is an optimization technique somewhat on the lines of dynamic programming, if you're familiar with dynamic programming from your algorithms course. And you can use it to speed up programs by caching or storing the results of expensive function calls. And rather than rerunning them again, you can basically just return the results if the same key is looked up. So we're going to use memoization in some pretty cool ways here in just a second, as you'll see. But before I talk about how we're going to use it, let's talk about the memoize class. So this memoizer class is a memoizing cache that maps a key, k, to a value, v, that's produced by a function. And this class is actually based on an example in the book Java Concurrency in Practice by Brian Getz and a bunch of other people. His implementation, from what I can tell, has a few bugs, but I cleaned those up, and I'll show you what my version looks like. The way this works is if a value has already been computed for a key, it's returned rather than having the function computed again. And I should have pointed out that the memoizer is given a function in its constructor. And so if, as we'll see in a second, if the key doesn't already have a value, then that function is called to compute it. If the key does have a value, we just return it without calling the function. So that's why it's an optimization. Under the hood, we use a concurrent hash map to minimize synchronization overhead. So that's what's used to implement this cache object. We'll see that in a second. And the concurrent hash map, as we'll see in a second also, uses FutureTask to ensure that only one call to the function is run the first time a key and a value are added to the cache. Now, when I show you the implementation, you'll see why we use the FutureTask. It's really, really cool. And the problem it solves is very subtle, and most people don't really even understand it's a problem. But we'll see how FutureTask makes that solution really cool. So that's why we're using the Memoizer to demonstrate the FutureTask. Now, another little fun thing here to understand is that Memoizer extends or implements the function interface. And I'll talk more about functions later. A function is part of Java 8, and it basically has a method in it called apply. And the way it works is that you parameterize your function with a value you pass, a single value you pass to apply, and that's t, that's the type of the parameter, and then r is the return value that comes back from apply. So it's really good for functions like isPrime or prime checkers, where you have one value that's the value to the function, and then you want a return value that comes back. So Memoizer is basically going to implement this function interface, and as a result, we can then use this to transparently customize other classes that expect functions to provide memoization optimizations. So, for example, in our prime checker program that has the Memoizer optimization, we're going to create ourselves a function called prime memoizer. Before we called it prime checker, now it's prime memoizer. And instead of giving it the brute force checker method reference, we're going to make a memoizer that takes the brute force checker as a parameter, and then we're going to pass that memoizer into the prime callable class, or instance of the prime callable class. And therefore, remember, prime callable simply says apply this function, and it doesn't know and doesn't care that the function it's applying isn't actually the brute force checker function. It's actually calling the memoizer. And the memoizer, as we'll see in a second, is going to do the optimization to look the value up and return a cached value if it exists, and compute the cached value, compute the value and cache it if it doesn't. So the nice thing is we're able to transparently parameterize the function while adding this additional optimization. So that's kind of the magic of Java 8, and that's how we're going to use the Memoizer. So let's talk about the actual implementation. This is really super cool. So here's Memoizer. It implements function. It defines a concurrent hash map. And this concurrent hash map is going to be used to check to see if we already have a value computed for a key. But to be really clever, we're going to define the hash map to have a key, k, and a future to v. And you'll see why we have the future to v in a second. It's really subtle, but it solves an otherwise thorny problem. All right, so just remember that the hash map is a mapping of key to future to v, where v is the value. We then define a field that stores the function, and that is what's set by the constructor. So you can see you pass the function in, that gets stashed away. We're going to use this if we look something up that doesn't already have a value. All right, so that's the fields and the constructor. Now let's take a look at the apply method. This is the guy that does all the interesting things. Apply is just the name of what's implemented from function. So we call apply, we pass in the key, and we're going to get back a value. So the first thing we do is we go to the cache. Remember that this is the cache. And we say, hey, cache, is there currently a future defined for this key? Yes or no? Remember, get is a super fast lookup on a concurrent hash map. It probably doesn't do any locking at all. It should just be something as simple as a compare and swap operation. So it'll return a value very quickly. If that value is non-null, then the future has already been created. And we'll see in a second how we get the result from the future. If the result is null, that means this is the first time in. This is the first time a key has been created with this value, with this, I don't want to say value because we got a value to mean something else. This is the first time this key has been given to the Memoizer. So if it's null, we're then going to go ahead and make ourselves a future task, FT, and we're going to give the future task's constructor parameter the the field that keeps track of the function to apply. So note, this is actually a lambda expression, right? So I'm not actually calling the apply method on the field mf, which stands for function. I'm giving it a lambda expression, which will be called later when I run this future task. So this is just good old Java 8 syntax for lambda expressions. So this isn't an actual call. This is giving it a piece of code to call at the right point in time. So now I've got a new future task. And now I'm going to go ahead and I'm going to put this future task into the map at this key. And put if absent is this really cool atomic operation that's defined on a concurrent hash map that will store this value at this key atomically if it doesn't already exist. So this gets around that race condition that would otherwise occur if we check to see if the key was there, and then, if not, put the key in there. That's called check then act. Check then act is evil in concurrent programs. So put if absent basically closes the race condition window by checking atomically inside this function if the key is there, and if so, it ignores it and returns the existing value. Otherwise, it goes ahead and stores that in the map. So this atomically puts this key in, and it puts it in, of course, once. Now here's the clever part. Put if absent returns a future. And if it returns a non-null future, that means the key has already been put, the value has already been put in that key. If it returns null, that says this is the first time in. So if it's the first time in, then we compute the function once. So this is the magic part, right? So we're going to go ahead and we're going to say to the future task, run your computation now. And we know that this is the only time run will be called if it's the first time in. So at that point, we're going to block, we're going to do whatever this run function is. For the prime number checker program, of course, it'll check if the number is prime, but we don't know or care at the Memoizer level. So this will then go ahead and run, and number one, we'll assign f to ft, and then we'll run that call. So just think about the different conditions that may have occurred. We might have come in here and found that we already had a future. If we didn't, we would go ahead and make a new future task. We're going to stick that in the map once. It'll only go in one time. And if that was the first time in, we actually run the future task. Yes, Marion?
Why would we check for null again?
Why would we what?
Why would we check for null again in the return?
Why would we check for null again? That's the gist of the whole thing. This check here is to prevent a situation where two threads show up at the same time. The value has not yet been put in the map. And if we didn't have this extra null check, we would end up running those computations twice. Now, only one of them would actually get stored in the map, but we wouldn't guard against multiple executions of that function. Now, for this program that we're writing with prime number checking, it's not the end of the world if we do the computations more than once. But you can imagine some other program where you don't want to have a value computed more than one time. If nothing else, it's just wasting computation, but it might actually have some side effects that could be harmful. So this way of doing things ensures there's only one time the function is created. And the reason it works is because we have the future task, and we've stuck the future task in the map atomically. So anybody else who comes in here is going to find it and not go through this path again. But keep in mind that because it's a future task, the actual value may not be available yet. So there could be a bunch of threads that come in. Only one of them will actually generate the function, but the other threads need to wait until that function is finished before they can get the value. So that's what we're going to show on the next slide. So the next slide is going to show how we're going to make sure all the threads block until the future is computed. Did you have a question, Duncan?
Back on the
Yeah.
So you do f equals ft and ft run. So
Yes.
you're running the thing again, but you're also, does that set the value post run to f?
Great question. You'll see why we do this when we look on the next slide. The question was, why do we say f equals ft and then ft.run? We could have done those in either order. It doesn't really matter. The key point here is that we are storing the future. Remember, a future task is a future, so this assignment is perfectly legal. We're trying to make sure that f, in this context, is pointing to something, and we want to make sure it points to ft. And you'll see why we're going to do that when we look at the next slide. So the next slide is the slide that, this is after all the code we just looked at, right? So everything else has been done. And now we're going to fall through, and we're going to say f.get. And here's the interesting part. If the way this was set up was that the value had already been computed and stored, and the future task computation was finished, then f.get will just return the value. So we're done. If this was the first time in, and we had a situation here where two threads came in at the same time, there wasn't a value, one of them is going to go ahead and run the computation, and the other one is not going to run the computation. We want to make sure that the future that this guy gets back, which has already been updated but not finished yet, will allow him to block until the thread that is running the computation finishes running. Right? So this makes sure that two threads that show up at the same time, one of which is going to run the computation. We want to make sure the other thread, which doesn't run the computation, waits until the first computation is finished. So that's that case. And then the third case, which is what Duncan was just asking about, was the one here, where we're the thread that's running the computation. And now, when we're finished, we just want to make sure that we get the result of our own computation. And so that's what that's doing. By setting f to ft for that case, after ft.run is finished running, then this guy will fall through, and he'll get his own result he just computed. So this handles all the three cases, right? We've already got a result, so we just read it. The result is processing but not computed yet, not finished, in which case we have to block, or the case where we are the ones doing the computation, and when we're finished, we'll get our own result. So those are the three cases that you have to think through. And the cool part about FutureTask is it's basically a placeholder for an unfinished computation. And by having it in the map, it allows us to be able to block these threads until the computation is done. But the computation will be handled in a graceful way. If an exception occurs for some reason, we go ahead and remove the key from the map. So that just cleans things up. OK. So that is the Memoizer, and that's the end of the Java FutureTask discussion.